It is.
a good chunk of my time, I was well. It's like
Oh, okay, I do.
I was gonna say it was just oh my gosh, what's the word? Molecule with a reaction of E minus, and then you're supposed to draw it afterward. You didn't get like
That
an
is
actual like
that is
EMR.
what mass spec is. Mass spec is when you remove an electron and then create this charged particle that you can bring to a detector, but based on its mass, it hits the detector at a certain spot.
I think
Oops,
that's what I was
sorry.
waiting for was like
It's showing people's answers.
was the mass spec readout.
I did something wrong when I got to this, so I think I'm going to get to this a different way. So I can see the confusion in how it's written. What confuses me looking at problem 38 on the OCHM 1 review is the big arrow. Usually a wide arrow represents a retrosynthesis. What can this come from? But it's not closed at the top, at the end. And this is closed. So it's really strange. This is not technically a chemical reaction. I think this rides the fence between what do you call chemical and physical, because all you're doing is pulling out an electron without necessarily changing the chemical itself. You don't. Well, you do break a bond, though. You break a bond. There is more than one answer to this, but we'll talk about mass spec a little bit. So in the instructions it says draw the molecular ion. That should be all you need to know what to draw. Draw the molecular ion. Although technically it should say draw a molecular ion because there are many that exist. There's just one that is predominantly formed. All right. So today we've got all the best stuff to cover, all in one day. And that's kind of how my OCHM 1 class felt last night. I went through an entire section. We covered polarity and IMFs and introduced nucleophiles and electrophiles and electron arrows and resonance and equilibrium and pKa in one class. And then I said, go home and have fun on the unit test. However, I actually have made some modifications to the unit test. I think it should be doable. I'm also making modifications to your unit test because I've gotten feedback in the past. It's not really a good representation of what we do in the first few weeks. And I am like 40% done with those modifications. So after class, I have homework to do. And so for whichever one of you wakes up at 8 a.m. and says, I'm going to do my unit test, it will be ready. And I think it will reflect what we've talked about. It will be doable. It's going to be a good time. All right. We left off in kind of a weird spot yesterday talking about molecular descriptors. Words that we use to describe molecules. Can you guys remind me what those words were? Good. Chiral is one. Achiral is another. Meso is a third. How many molecules do you need to have in front of you in order to use these terms? Just one. There's a similar concept in molecular relationships. One relationship that's predominant in organic chemistry is structural isomerism. Structural isomers. Anybody want to try and give a definition of what makes two compounds structural isomers?
The chemical formula is the same, but the connectivity differs.
Good. Anybody add anything to that? Same chemical formula, different connectivity. Connectivity, sorry. So the simplest you can show is something like pentane and 2-methylbutane. Those are structural isomers. But then you could get more complex, and you could take 2-butanone and tetrahydrofuran. 4 carbons, 1 oxygen, and 8 hydrogens. These two share the same chemical formula, and because of that chemical formula, they share the same degrees of unsaturation. Anybody remember what degrees of unsaturation tells you about a compound? Kayla? Not exactly the carbon to hydrogen ratio, although that would be impacted. James? How many pi bonds and or rings? And does degrees of unsaturation indicate whether it's a pi bond or a ring? No, because these two are structural isomers and they have the same degrees of unsaturation, one pi bond or one ring. I don't think that you'll have to calculate degrees of unsaturation in this class, but I like the degrees of unsaturation equation, so I'm just going to give it to you. It's the two chicken rule, twice the number of carbons minus the number of hydrogens and halogens, plus the number of nitrogens and 2 divided by 2, start with 2, end with 2, divide by 2, subtract 2 times, add 2 times, and it spells chicken. So it's the two chicken rule, and you plug that chemical equation or chemical formula into that equation, and you will know how many rings and or pi bonds your compound has. If you're working with something like spectroscopy, then you can actually start to predict, will I have pi bonds? Should I look for pi bonds, or am I fully saturated? Every atom is bonded to as many unique atoms as possible. You'll notice that one of our most common elements is not listed in the two chicken rule. Which one? Oxygen's not there. And that's because for every oxygen you place into a molecule, it brings with it enough hydrogens, or it bonds in such a way that it doesn't unsaturate the molecule ever. Whereas halogens replace hydrogens, so you have to count for them. Nitrogens bring with additional bonds. Interesting. All right. What are some other, what's a broad term for molecular relationship that you guys remember? Another type of isomer. Yeah, constitutional is structural. The constitution of it, the way that it's built, is different. Conformational isomers, which we're actually not going to talk much about at all, and I refused to even introduce the term the first few times I taught because I didn't like the term. But conformational isomers, really, they're exactly the same except for how they're conformed in space. So if you're looking at perhaps transbutane, this is one conformational isomer, and as I rotate around a Newman projection, I can get a different conformational isomer. Which is also to say that things like this, an S-transdiene and an S-cisdiene, are simply conformational isomers. They've rotated around in space differently, but they're the exact same molecule. Good point, Kim. Another type of relationship. Regioisomers. Maybe sounds like structural. Just where on the molecule? Stereoisomers. Is this what you were thinking of, Brett? Good. So we've got some big names here: enantiomers and diastereomers. Now I know that this word trips up a lot of students, so I'd actually like to say it together. I'm going to say it and then have you repeat it with me. Diastereomers. Diastereomers. Get a lot of students that go diastomers, and I get it. What's a diastereomer? Diastereomers. Can you tell me what the relationship is between two molecules that are related as enantiomers? Mirror images that cannot be superimposed. Everything has a mirror image, but a lot of things can be superimposed with their mirror image. Meso compounds, for example, have a mirror image that is superimposable with itself. But if your mirror image is non-superimposable like your hands are, then they are enantiomers. And how do you define diastereomers?
Stereoisomer is not an enantiomer.
It's not a mirror image, but it's also not superimposable. So usually, not usually, to have a diastereomer, a compound must have at least 2 stereocenters. One of those stereocenters stays the same, and one of those stereocenters changes, at least. There is another class of stereoisomers that sugars use a lot called epimers. Anybody heard of epimers? Maddie, you have?
I have, yeah, but it's a hot minute ago.
Epimers are stereoisomers that differ in their chiral centers by only one position. Only one position is different between them. So I want to say D and L sugars are epimers of each other. All of their chiral centers are the same except for the last center. All right. Now Brett did bring up an important word that I just want to talk about quick, which is regiochemistry. Because we are going to talk about regiochemistry more this semester than we will stereochemistry. Anybody want to try and define regiochemistry? What does it make you think of in your head? I know for those of you who didn't have my class before, you might not have learned this term much. How about it? People that weren't in my class before, do you know this word?
I know I should know the word.
You know you should know it? You've heard it, but you don't think about it much. And those of you that were in my class, do you think about it much?
I did. Tried to know it before the final. That was traumatic. So repressed it a
When
little.
I clearly didn't know what it was.
Well, what do you hear in there? Region. So it's literally just saying this part of the molecule or that part. So oftentimes regiochemistry comes down to looking at degrees of substitution or positions next to specific functional groups. I'm abbreviating here my aromatic ring. Instead of alternating double bonds, I'm abbreviating it with a circle, and we'll explain that more next week. So regiochemistry comes down to degrees of substitution, carbon substitution, most often. Can somebody name one degree of substitution that this compound has? Tertiary, right here, which we describe as 3'. Tertiary is a carbon that is bonded to 3 carbons. And there's actually, I need to make a small change, which is, I'm going to add 2 methyl groups there. Somebody else give me another regiochemistry label here. Quaternary, the one that I just drew in, a carbon that's bonded to 4 other carbons. Another. Primary, and that would be prevalent in this example, a carbon that's bonded to only 1 other carbon. We also call primary carbons often methyl groups because they're usually CH3s, maybe not always. And the last one, secondary, a carbon that's bonded to only 2 other carbons. And the regiochemistry can actually explain a lot of things. We're going to look at reactions here in a minute, and we're going to look at more substituted carbons versus less substituted carbons, and how that impacts the regiochemistry of the reaction. Now you'll notice I didn't label any of the alkene carbons or benzene carbons with these labels, and that's because I've not seen it done often, and I find that it's a bit confusing. Because here's a carbon that's bonded to 2 other carbons, but it has 3 bonds to carbon. because it has a double bond. So do you call it secondary or do you call it tertiary? And then once it reacts and loses one of those bonds to carbon, what do you call it then? So I often will look at alkenes or benzenes and just say, is it more substituted or less substituted? Does it have more carbons, more substituted, or does it have less carbons bonded to it, less substituted? Then the other regiochemistry term that's going on here, we've got these positions adjacent to the alkene, which are called allylic, as opposed to being bonded to the alkene. Anybody remember what it means to be bonded to the alkene? Vinylic. A vinylic chloride is different in its chemistry than an allylic chloride. We don't really have a term, well, I guess we do. Being bonded to the aromatic ring has a different name than being bonded next to the aromatic ring. Anybody remember either of these? Which one? Benzylic is one of the terms, that's correct.
There's two away, methyl's one away?
Methyl is one away? No. Methyl is a CH3. Benzylic. Attached to the ring of the benzene or attached off of the ring of the benzene? Yeah. The benzene ring has carbons that are carbons attached to it that are benzylic. So then if something is attached to the benzene, we call it aromatic. Okay. Good vocab lesson. Always good to get those gears turning before we look at reactions. All right, what I'm going to do is draw a big diagram that has all of these reactions coming off from it so that we don't have to do it as a list. However, not every reaction is highlighted well by the same starting material, so we'll break these up into a couple of parts. First, actually, we'll look at the reaction that doesn't relate to any of the others, and that is radical halogenation. An alkane can be reacted with Br2 and light, H nu. Notice the regiochemistry of the product. Is it the least substituted alkyl halide that forms or the most substituted alkyl halide? Good. When you write down things about reactions, I think you should write down things about its regiochemistry and its stereochemistry. The stereochemistry here would be random. That halogen adds on either face, but there's actually no chiral center formed here, so it's not relevant. When we look at this reaction in the context of benzylic and allylic positions, things change. The benzene stabilizes the radical intermediate through resonance. The most substituted carbon only stabilizes the radical intermediate by moral support, as I call it. Electron density helping to fill the gap that that one electron has. So the most substituted carbon typically kind of hides that electron and makes it less reactive, stabilizes it. But benzene can delocalize that one electron, which stabilizes it. So notice allylic and benzylic radical halogenation, it does not go to the most substituted carbon. It goes to the allylic or the benzylic position. Deal? You know what? While we're on the topic of reactions that just don't have a bunch of things spiraling off of them, let's look at the Diels-Alder reaction. Our simplest Diels-Alder reaction needs a diene in a specific conformation. We call it the S-cis conformation relative to the sigma bond. The dienes are cis to each other, S-cis. And this goes through a cycloaddition reaction. Addition reactions consume a pi bond. That's the definition. Addition reactions consume a pi bond. This is going to be strange because it actually consumes two pi bonds by way of transforming one pi bond into a ring, or transforming a degree of unsaturation from a pi bond to a ring.
On the first radical going on to the alkane,
Yeah.
so they're just kicking a hydrogen off.
Kicking, actually a lot of textbooks use the word abstracting a hydrogen. Bromine gets split into two radicals. One of those radicals takes the hydrogen, leaving behind the carbon radical.
Oh yeah, you hit the.
And the second radical, second bromine radical, terminates with the carbon radical to form the bond. Diels-Alder reactions can be predicted like this. A six-membered ring will form. A double bond will always result between positions 1 and 3. And the arrows are interesting, if not a little convoluted. There's an attack from 4 to 5, from 6 to 1, and then this shifting of electrons between 1 and 2 to come down between 2 and 3. And then it can get really complicated. It doesn't need to be an alkene. It can be an alkyne. And then oftentimes, those groups have other groups coming off of them. So as an example reaction, if you took the OChem 1 labs here at SLIC, then you ran this reaction. The Diels-Alder synthesis of nadic anhydride. But notice how 1 and 4 are S-cis locked like that because they're in a ring. And they share an atom in common, this like atom 5' that links 1 and 4. So I can start by labeling the 6 atoms of interest. And when I draw my 6-membered ring with the pi bond, I can figure out where those groups have gone. What I don't see is that 5th atom connecting 1 and 4. So I just draw it in. And maybe my line was a little bit too straight, so I'm going to put it at a little bit more of an angle so that I can see very clearly there is a bend there. And of course it has some stereochemistry, so it's either coming up or going down. It's either wedged or dashed. And then 5 and 6 are bonded to each other. I just can't show it because I ran out of space. Or excuse me, 5 and 6 are bonded to something else. 5 and 6 each connect to a carbonyl, and those carbonyls are connected to each other by an oxygen. So there's my final product, a polycyclic structure. Two cyclic structures react to make a new cyclic structure, polycyclic.
Why is it that the right atom's alkene wants to go with left atom's alkene? And so why does it go towards or past the 2 alkane carbons and goes right to the alkene? Why doesn't it flip it around and bond to that side?
I'm not sure I understand your question. Why does this alkene attack this alkene?
Isn't it hard to push those two atoms up? Or I guess that one atom up, sorry?
No. But also, this atom doesn't have any reactivity as it is. So,
And then I've been in classes where for that part that pops up, you have to draw which side is forward. Does that matter here?
we're not going to focus on it for our class, but there are actually two diastereomers that form. This carbon is wedged while these carbons are also wedged, or this carbon is wedged while these carbons are dashed, or vice versa. Those are diastereomers because they're non-mirror images and they're non-superimposable. Although some people call them geometric isomers because any stereoisomer of this compound is meso. There's this mirror plane that cuts through the middle of the compound. So they are diastereomers, but specifically they're diastereomers on a meso compound, which, oh no, actually I think I'm confused. There are achiral molecules that have diastereomers. One for dimethyl cyclohexane has no chiral centers because the plane of symmetry cuts through those atoms, but they can both be wedged or they can be opposite, cis and trans. Those would be geometric. Oh, alkenes are also geometric isomers, cis and trans, without being chiral. Anyways, diastereomers for sure. Okay, we're not going to have to get into it too much, so you're lucky there.
I appreciate that
Mhm.
because that was really stressful before.
All right. Radical halogenation, Diels-Alder, those are some of the most obscure ones that you ran into in OChem 1. Let's go back to looking at our alkene addition reactions. So in the middle of a bunch of different reactions, I'm going to draw 3-methyl 1-butene. If you don't already see it in your head, I want you to try and draw that. 3-methyl 1-butene. Okay. Oh, I didn't draw this in the middle. I'm sorry. Did you get this? 3-methyl 1-butene. Great. All right, I'm looking at the list that I've got on your learning objectives for this unit. And I've got 11 reactions to show. So I think what I'm going to do is I'm going to put these in 8 reactions from this, and then we'll do the other 3 reactions separate. Deal? So in order to do this, let's have one reaction straight up, one reaction straight down, one to the right, one to the left, and then we're going to bisect each of those cardinal directions. 8 total. We could try to squeeze 11 in there, but then it just gets really messy. All right. In no particular order, other than just what feels natural to me. First, hydrohalogenation, HX addition. We're going to look at some mechanisms for some of these after. This is a carbocation intermediate reaction, which means that the most stable carbocation possible will form. Primary carbocation is less stable then a secondary carbocation. So the secondary carbocation forms. Adjacent to this secondary carbocation is a position that would be even more stable. So a hydrogen shifts over and leaves the carbocation on the tertiary position. So my product is 2-halo 2-methyl-butane. If this were HBr, then it's 2-bromo 2-methyl-butane.
Is it like the way the electrons react with each other, like shielding and stuff, instead of bonds? Never mind.
So actually, we can make this quick assumption on this molecule and say that there is partial negative character on the less substituted carbon and partial positive character on the more substituted carbon. I just introduced electron arrows to OCHEM 1 last night, and the rule that I keep going back to on electron arrows: bonds break to the partial negative atom. Why is that atom partial negative? Because it owns the electrons. So when a bond breaks, who gets the electrons? The partial negative atom. I almost always have students that say, isn't it negative? Shouldn't it repel electrons and push it away? No, it's negative because it's already pulling on them. And bonds form from the partial negative atom, because who can use electrons to make a bond if not the atom that owns the bond? So these are my two rules when you're showing arrows. Break them towards the more negative atom and form bonds from the more negative atom. Now, if you feel like it's odd to say that there's partial charge across the carbon-carbon bond, that's normal, because we would say their difference in electronegativity is 0. But we can draw two resonance forms of this alkene. One of them is more stable than the other. The negative charge on the less substituted carbon experiences less electron repulsion, and the positive on the more substituted carbon experiences more stabilization. So we can actually use this to predict how electrons are going to move. All right, second reaction, HX ROOR. If you want to be specific, you can use H2O2. ROOR is a peroxide. So on your learning objectives list, I've labeled this as hydrohalogenation in peroxide. Now we already know what happens with HX addition. What's the usefulness of adding a peroxide? Exactly. Changes the regiochemistry of the product. Here, we get a less substituted addition. This would be something like 1-bromo 3-methyl-butane. And it's in result of the radical intermediate that exists there.
Does the hydrogen want to leave the peroxide because the oxygen is more comfortably negative, and it just goes onto that?
The hydrogen doesn't leave the peroxide. The peroxide creates radicals out of HX. HX radicals, the X radical, then creates a radical on the carbon, and then the carbon radical propagates this circle.
So you mix those two first, and then you add in the reagent.
Sure. I don't know. I've never actually run it, but I would assume you'd mix them in. Yeah, you know what? I'd probably mix the peroxide with the alkene and then add the HX reagent. I don't think I'd add HX with peroxide to the alkene. The peroxide and the alkene shouldn't do much to each other, but the peroxide and the HX will. So when you're ready for peroxide and HX to do something, add the HX then. Now there is regiochemistry terminology named after a dead guy from a long time ago. When the hydrogen adds to the less substituted carbon, the carbon with more hydrogen, we call it Markovnikov addition. When the hydrogen adds to the less substituted carbon, we call it anti-Markovnikov. So you're welcome to do that. I don't think that we will need those terms much this semester, so I'm not going to lean into them much. Going from HX, let's look at X2. Now, I'm not generally going to have a solvent here, but oh no, I forgot one on your list. Isn't that a shame? Yeah, I'm going to have to add it. Sorry. If the solvent is not listed, or if the solvent is listed as like THF or ether, then it just means that all you're paying attention to is X2. All we do here is add 2 X's across the double bond. Now it's hard to show it on this because I form 1 chiral carbon and 1 carbon that is achiral. So the conformation of the achiral carbon doesn't matter. But this reaction doesn't have regiochemistry, it has stereochemistry. This is an anti-addition mechanism. The 2 groups will add 1 up, 1 down. And when we look at the mechanism later, it will make sense why. If the solvent is listed with X2, then it's either listed as ROH or as H2O. So I'm going to show you what 2 products form from this. Instead of 2 halogens forming, I only get 1 halogen, and then I get either an ether group or a hydroxyl group. Notice the relationship, ROH/H2O, halo ether / halo hydrogen. Your solvent changes the functional group. Water leads to an alcohol, but an alcohol leads to an ether. I get a lot of students that have the alcohol as their solvent, and they show an alcohol in the product, which means that somehow the CO bond broke, and not the OH bond. But the OH bond is much weaker than the OR bond. OR stays. Questions? Brett, is that reaction regiospecific? It is. The solvent always adds to the more substituted carbon. So I'm just going to draw attention here. There's no term for it because Markovnikov died before he realized that his rule only applied to hydrogen. And so you can't say that all regiospecific reactions are Markovnikov. There's no hydrogen addition here. But it is still regiospecific. Solvent adds to the more substituted carbon. Is this reaction stereospecific? Meaning similar to X2 halogenation, does this form anti? Do the 2 groups add opposite of each other? They do. They follow a nearly identical mechanism. The only difference being what nucleophile attacks in the second step.
What's the... I thought trans was for groups
Mm.
and not
I'm
stereo.
sorry. I meant to put anti. The semantics between anti and trans is minute. But trans is a locked configuration. Trans says these 2 things are always opposite. So you can have trans groups on a ring because they can never rotate, and you can have trans things on an alkene because they can never rotate. But on a structure like this, you can rotate. So they're not always going to appear trans, but they add anti. That is stereospecific. Thanks for catching that. Does that make sense? The similarity and distinction between anti and trans?
There's got to be some push to whether or not the other group is up or in the chain, right?
When they form opposite of each other. One adds to the top face of the alkene, the other to the bottom face. Then they can rotate through a conformation to the lowest energy conformation.
Like, you mean trans or cis? Or are you referring to stereochem?
Their stereochemistry is anti when they form.
What about trans and cis? Because this one is cis, but does it ever
Anti. Anti.
Or what am? Do you know what group I'm trying to say?
Syn?
Yeah.
Syn addition?
Yeah.
These reactions are not syn addition. We'll get to those. All right. The first of 3 hydration reactions. Acid catalyzed hydration. Now we wrote the acid, Luis, as, what's the acid here? In H3O plus H2O. What's our acid? Nope. H3O plus. Because remember, the more positive thing is the better acid. But you don't need to use H3O plus. This can be written as H plus. It can be written as H2SO4. You can use other types of acids. But generally, this is how you'll see it written for me. The product that we get is 2-methyl 2-butanol. Is this reaction regiospecific? Yes. Hydrogen adds to the less substituted carbon. What does this reaction have in common with HX straight across from it?
Involves a radical.
Not a radical. The most substituted carbon does have the product, but actually it's not even one of the carbons of the alkene that gets the new functional group. Carbocation rearrangement occurred. So Jacob, I think you were thinking a radical will cause the rearrangement, but actually there's a radical in this reaction that forms on the more substituted carbon, and it doesn't rearrange. Radicals are inert to rearrangement. Carbocations, on the other hand, a vacancy of electrons, that can have people move around. Okay. Our next, and I apologize about the colors. Maybe I should have done the arrows in those bright colors, and I'll switch that for the next set. Our next hydration reaction is 2 steps. First, HgOAC2 with H2O, followed by NaBH4. That is oxymercuration reduction. You hear mercury in the name, but you also hear oxy. Oxy, like oxidation, so you need a second step, that is reduction. Oxymercuration reduction. This is one place where I take off points if you do not have 1 and 2. Because like Killian was saying earlier, if you dumped all of the reagents all together into a flask, you don't get the product you want. This reaction has the same specificity, the same regiochemistry as our first hydration. It's Markovnikov, but it avoids carbocation rearrangements. There is not a carbocation intermediate. Our last hydration is also 2 steps. First, BH3. Second, basic aqueous hydrogen peroxide. H2O2, NaOH, H2O. Basic aqueous peroxide solution. Now we've already done Markovnikov twice add the OH to the more substituted carbon. And we did it in two ways, with rearrangement, without. So the only benefit of this reaction, anti-Markovnikov. 3-methyl, 1-butyl. All right, the last one for this set is syn-diol addition. OSO4 or cold potassium permanganate. Those of you that have done the labs here at SLIC, the OCHEM 1 labs, you have run cold diol addition with potassium permanganate. When we did the dehydration of 4-methyl cyclohexanol, we wanted to prove that an alkene had formed, so we mixed in room temperature potassium permanganate, and we watched as the purple potassium permanganate disappeared and the brown MnO2 precipitated out. We had diol addition, dihydroxylated our alkene. So here's what we get. 2 alcohols across the carbons of the alkene. And this is a syn addition reaction. Not anti, but syn. Meaning that if this was on a ring, the groups would be cis. But because it's not on a ring, they're not inherently cis. They can rotate free through any conformation. But they do add to the same face, syn. Similar to cis, but not cis. Do you guys mind if I erase this so I can leave that up for a little while? Okay. Any questions on these reactions?
I thought cis referred to like what side the big groups add on to. It referred specifically to an alkene.
Syn. Cis means are 2 groups on the same side of an alkene or are 2 groups on the same side of a ring. Syn means that they add to the same face of an alkene. Do you agree? Okay. All right, for the last one, I'm going to change our structure because it will be useful to have a slightly different structure for a few of these last ones. And here we actually only have 4 reactions to consider. Kind of on the vein of adding oxygens across the alkene, let's first look at epoxidation with MCPBA or any generic peroxy acid, RCO3H. We are going to learn in our next section about how to interpret that name, MCPBA, in our nomenclature on benzene. Any peroxy acid will do here. MCPBA is just kind of an OCHEM fan favorite. But this gives us an epoxide. And if you know anything about physics, this has to be a syn addition. If one arm goes up and the other arm of the epoxide goes down, then they would actually just meet in the middle, and that would break the rules of bonding, so syn addition is the only way it can work. Our next reaction takes us on a whole different route, hydrogenation, H2 with palladium over carbon. If you took our OCHEM 1 labs here, you ran this reaction on an unsaturated fatty ester. We hydrogenated its alkenes and made it a saturated fatty ester. And I will say it doesn't have to be palladium. This can also work with nickel and platinum. But the product here is just an alkane. Maybe the worst bond line structure I've drawn all night though. So don't copy that. That looks much nicer. The last two reactions on our alkene are very similar to each other. They're both oxidative cleavage reactions. First, O3 with DMS or zinc. Now DMS is this compound, dimethyl sulfide. There are places you might see that it's listed ozone then DMS or ozone then zinc. Sometimes 1, 2, and other places that don't. And I've never run this reaction either, so I'm not quite sure what to give you. This is a cleavage reaction, which feels counterintuitive to calling it an addition reaction. But we get two groups. Both carbons of the alkene are now carbonyls. Notice what happens when a carbon of the alkene is bonded to two carbons. It becomes what functional group? A ketone. And notice what happens when a carbon of the alkene is bonded to one hydrogen. It becomes an aldehyde. By the way, how are you feeling about your functional groups? They're going to be on the unit test. And I know we haven't had a ton of time to explicitly talk about them, but we're talking about them now. Do you know where to find a good resource on functional groups if you need it?
Your homepage.
Canvas homepage. I've got that big list. Make flashcards. Do whatever you need to do. Apply them to your compound. Get familiar with functional groups. Our last reaction is oxidative ozonolysis, which we either run with ozone and hydrogen peroxide, or we run it with hot potassium permanganate. And what a shame, I kind of ran out of space. We get two things again. One group from each carbon of the alkene. Notice what functional group forms if the carbon of the alkene is bonded to two carbons. Ketone. That's the same as reductive ozonolysis. But notice what happens if that carbon is bonded to one hydrogen. What functional group forms now? A carboxylic acid, not an aldehyde. This is the oxidative versus reductive nature of the two reactions. Oxidative ozonolysis will oxidize the carbon further. Reductive ozonolysis leaves it more reduced than oxidative. Less oxygens attached. Now the reason I drew DMS down below is because it makes Brett's favorite compound at the end. DMS or zinc, they take that third oxygen and they oxidize themselves into DMSO or zinc oxide. In oxidative ozonolysis and this other oxidative cleavage with potassium permanganate, it's a little less straightforward where all of the oxygens go because you've got this peroxide that's doing some fun stuff. But here it helps students, I've seen it sometimes, to say, where does that third oxygen go? Gets pulled out with the reducing agent. All right, any questions on our alkene addition reactions? Any that you felt were missing? Any that you felt were not supposed to be there? Don't answer that. Okay.
Is that 2-methyl-2-butene?
Yes, 2-methyl-2-butene. All right, I want to look at some reactions with alkynes. And to do this, we're actually going to take two different alkynes and split them into a similar reaction, but like this. And I've got 9 reactions to show us. 4 that definitely need to go for the one on the right, and 5 that need to go to the one on the left. So we're going to draw 4 reactions here. And that's going to be, oh, you know what? I think we can do them at kind of different angles. And then we've got 5 reactions to consider on the left structure. 1, 2, 3, 4, 5. A lot going on at the moment. We'll start out similar and look at hydrohalogenation with this compound on the right. If we use HX, we can actually get 2 things that form. A 1 equivalence addition and a 2 equivalence addition. Does it make sense, the 1 equivalence and 2 equivalence addition? First, I add 1 H and 1 X, then I add a second H and a second X. This is regio-specific in 2 capacities. It's Markovnikov, and the second HX addition puts X in the exact same spot. So whether this is a terminal alkyne like this or an internal alkyne, you always get a geminal dihalide, twin dihalide. Similarly, if we do HX with peroxide, then we can get a 1 addition HX and a 2 addition geminal dihalide HX. By the way, I just want to say I know a lot of you are formatting this in a way that works for you, doing some sort of list. That's great. Keep it up. Even take this home later, review them, reformat, however you need to do it. Next, on the right here, I want to look at oxymercuration. Notice that it's not oxymercuration reduction. And we're using mercury sulfate, sulfuric acid, and water. 1 step, not 2. This reaction adds an equivalence of water. It's a hydration reaction. And it's Markovnikov. It adds H to the carbon with more H. Then we have anti-Markovnikov addition. Hydroboration oxidation. 2 steps required. And some people with alkynes, they use a reagent that is not borane. They use a borane derivative that messes with the alkyne a little bit less, makes it easier to run. Being a hydration reaction, it adds 2 equivalents of H2O, but it adds an anti-Markovnikov. Ketone versus aldehyde. Now, to stay on the chain of carbonyl formation, Let's look at oxidative ozonolysis. There is no reductive ozonolysis. We're taking this one here this time, and we're showing that it will form two carbonyls from both sides of the alkyne. In this case, it's symmetric. I get two equivalences of the same compound. But if my alkyne was asymmetric, I would get two carboxylic acids. Let's take a brief detour to look back at halogenation. This is a bit similar to our hydrohalogenation, where I can do two equivalences. The first equivalence is anti, and the second equivalence doesn't really matter because it forms achiral centers, a tetrahalide compound. Do you know what the last three are? They're all the same type of reaction with different outcomes. We did hydration already to the ketone and to the aldehyde. I see a lot of you comparing it to this side. That's not a bad idea. We won't have diol addition. No. We've got.
Could it by chance be partial metal and ammonia?
He's looking back at his notes. The last three are all hydrogenation reactions.
What?
H2 with PDC runs full hydrogenation down to an alkane. There is no way to pause the reaction and do one equivalence, two equivalents. H2PDC does two equivalences. But if you run this with Lindlar's catalyst, then you can pause the hydrogenation at one equivalence. Despite being called a catalyst, this actually contains a poison. It poisons the reactivity of the alkene. We know that alkenes can do hydrogenation, don't we? Wait, that scared me. We know that alkenes can go through hydrogenation with H2 and PDC. So Lindlar's catalyst poisons the reactivity of the alkene. Notice the stereochemistry. Syn addition. The two hydrogens add to the same face. And lastly, we can do metal in ammonia. Notice that this is Na with nothing bonded to it. You can even put Na comma to make that seem more separated. How many electrons does Na comma have in its valence shell? 1, because it's not an ion yet. It is a highly reductive reagent. It wants to get rid of that electron. But the byproducts that form are not reactive to the alkene intermediates. Now there is a part of this mechanism that can be used to verify why it gives a transalkene, and that's because of electron repulsion. In this trans configuration, there's a lone pair and a radical that are separated from each other as much as possible, and those experience the most electron repulsion. That's why it's stabilized in that trans configuration. Whew, we Blew through those. Good work. Let's take a brief 5-minute break before we come back in to look at some more reactions, mechanisms, and spectroscopy. There's more.
Substitution and elimination?
Yep.
Besides those. No way. Yeah. Aldehyde is just an oxygenless carboxylic acid.
What? An oxygenless carboxylic acid.
Or what? A non-alcoholic.
Carboxylic acid is an alcoholic aldehyde. No, because there's no alcohol in a carboxylic acid.
Yes.
Says who? Me.
Yeah. Do I need like 100,000 chemists to agree with me?
No, you need IUPAC.
They're not
If you
gonna
can get
say-
IUPAC to agree with you, then I'll agree with you.
IUPAC? Who gave IUPAC authority? Was it the 100,000 chemists?
That's a good question.
It's called dibs, right? If you go first, probably.
See, huh?
Yeah.
I think they might have called dibs, yeah. And they gave themselves a really nice name. International Union of Pure and Applied Chemistry. What makes chemistry pure?
Ideally, all your reactants. What? Do they
They
assume?
define mixture, I think. So, like, it's not about a pure sample. I think they're saying pure chemistry and applied chemistry.
Do they assume that everyone uses dirty, contaminated reagents?
No, I think what they're saying is you can apply chemistry in the context of biology, in the context of material science, in the context of a lot of things. You can apply chemistry. That would be applied chemistry. But what is pure chemistry?
Yeah. Are they saying everyone's like dirty, bad chemist?
No, I'm saying it's not in an applied context. So it's not applied to some other field. It's just chemistry for chemistry's sake.
What do you think the pure is for?
Not applied. It's the International Union, IU, of Pure and Applied Chemistry. So there's two types of chemistry. There's pure chemistry and there's applied chemistry.
So pure. Oh, of just chemistry and applied chemistry.
We'll be honest, I prefer his theory of like dirty, rotten chemists in the corner that we're trying to.
Maddie, it's bold of you to take somebody else's side besides mine.
Fair point. Recent. Never said anything.
No, actually, I'm open to the discourse, but
Do you work for IUPAC?
I don't.
Are you?
I don't.
Taking cuts under the table, Greg.
Oh, I wish.
Don't we all?
Do you pay them to like boost your rate when professor grades?
Do you think I'd work as many hours as I do if I was taking pay from my UPAC under the table? No way. I'd be like, I had one class a week. That's it. One class a semester. No, I actually started a proposal. Maybe it was just in the spring. I started a proposal to submit to IUPAC to convince them to remove name reactions. So that's things like the Wittig reaction, Bayer-Villiger oxidation, Clemenson reduction, Wolff-Kishner reduction, because they do nothing. It explains nothing. It's useless. We could instead say hydrazine reduction. Do you know what hydrazine is? No, but I bet I could show you it, and you would be like, oh yeah, that's hydrazine, and now I know because of the name that I'm going to use that chemical. But instead, I have to tell you it's Wolff-Kishner reduction, which uses hydrazine, and now you need to know all of those things. And Wolff-Kishner doesn't help you remember hydrazine is involved. Clemenson reduction, you could just say it's the iron, mercury, I forget what it is, mercury, zinc in acid reduction. There are better names. I know there are.
I'll sign your petition. This is a start.
Thank you.
It would help with studying.
What is it? Ornithology tried doing it, making a push to get rid of bird names. Yep. But
Wasn't the Audubon Society that pushed for it?
they met some pushback because in like their international governing bylaws, it says names do not have to make sense. And they agreed to that.
Makes more sense.
And so they said, we're not necessarily going to do it.
What birds are named after people? Oh, are you erasing that?
A lot.
No, I can leave it until later, but then I have to erase. Or I guess I can just hide. Do you guys need this page still? I don't know why I thought that was going to cover it.
Main names
Oh,
that are
yeah.
people?
Lindler's catalyst is quinone and barium carbonate, I think. Although I think I just looked it up and it's not. Maybe it's barium sulfate. But it's just a mixture of chemicals that interact with alkenes in such a way that inhibits their reductive capacity. So it poisons the alkene from being reduced. Isn't that weird? And to be fair, I'm just now complaining about names, but Lindler's catalyst is actually a lot easier to remember than the actual chemicals that Lindler uses. So in that sense, I actually agree it kind of makes sense. If I showed you and had you write them out every single time, you wouldn't be as happy as writing just Lindler's cat.
So should we just include a list of ones we no longer want people's names on? With a clause that's like,
Good.
I don't hate y'all.
Great
I
point.
think you're great chemists,
You make a great point.
but your name's ridiculous. And we need to stop saying it.
All right. Reactions with alcohols. I'm going to try to set this up in a similar way. 1, we can take sulfuric acid and get the most stable alkene possible. That means acid catalyzed dehydration always forms the most substituted alkene and the trans alkene when possible. We can take tosyl chloride, which doesn't actually remove the oxygen's alcohol so much as transform the oxygen's alcohol into a different group entirely. It's now a tosylate group, which is a sulfonyl group. The oxygen is bonded to a sulfur that is in a similar bonding environment to sulfuric acid. So that oxygen can now leave more easily and is in resonance with the rest of that sulfonyl group. So this makes it a good leaving group, which means if you wanted to do some sort of elimination after this, you could now take tert butoxide, our big bulky base, and you could get a different elimination product, but it would take those 2 steps.
How are you going to format this roughly?
Square.
Is that coming around?
Yep. If we take HX, for instance, HCl and HBr, there's usually no preservation of stereochemistry. You get a racemic mixture. I drew it as a squiggly line, but you can just draw it as a flat line. It doesn't matter. The point is, if you had R2-butanol, you don't have R2-chlorobutane or S2-chlorobutane. You have both. But you can use thionyl chloride or PBr3, which will invert the stereochemistry at that chiral carbon. So there can be some chiral control, there can be some loss of chirality. All right, I want to look at alkyl halides as well, which can be such a beast to really sum up. So,
What does that squiggly line mean?
it just means it's not R, it's not S, it's not wedge, it's not dashed, it's both. First of all, I don't like the names SN1 and SN2 very much. I think that they oversimplify and also could be applied to a lot of different things. But we're going to be dealing with a few major types of nucleophiles this semester. So I'm going to show us this generic halide. If this reacts with something like water, it gives me an alcohol by means of SN1, which means that my chirality is destroyed. If I react this with hydroxide, it interacts by way of SN2, which means that my chirality is inverted. And then we have a number of other nucleophiles that are useful that pretty much all run SN2. These are things like azide, cyanide, and sulfides. That's N3-, Cn-, SH-. And these all give us SN2, inversion of stereochemistry. Some halides are better than others, but this semester we'll predominantly be using Cl and Br. Are you guys all right if I erase this picture? Do you need an image of it? Okay. Then we have elimination of alkyl halides. And again, this feels like such a simplification of the things that can happen. I'm actually going to take one of the, should I? I'm going to take one of the compounds that's on that practice sheet I gave you. And I'm going to show how there's 3 different ways you can run elimination with an alkyl halide. I'll just put X here though. if you take a weak base, weak nucleophile, like water or an alcohol, and I am sorry, I wanted to show also I showed water over here, but you could also do an alcohol, which is fairly important because again, water leads to an alcohol, but an alcohol leads to an ether. And in the same way that you can use hydroxide, you can use an alkoxide. Water leads to hydroxide leads to an alcohol. Alkoxide leads to an ether. Here, if I use something weak like water or an alcohol, I will get the most substituted elimination product possible. That's going to be between the leaving group position and the tertiary beta carbon, 1,2-dimethyl cyclohexene. If I use something small and strong, like hydroxide or an alkoxide, I do get the most substituted elimination product possible, but it has to be antiplanar. This halogen is dashed, which means antiplanar to it is wedged. There's no hydrogen here that's wedged. That's only here. And so I get 2,3-dimethyl cyclohexene. This is a tertiary alkyl halide, which means that I have one last position. And if I use tert butoxide, I will get only the least substituted elimination product. This gives me 1-methyl-2-methylene cyclohexane. So 3 main types of bases. E1, E2 with a small base, Zaitsev elimination, and E2 with a bulky base, anti-Zaitsev elimination. Questions on that? Now, to be fair, in these unit test questions, you will have to tackle them from every direction. Have a reaction shown where you need to find the reagent, the starting material, given the reagent and the product. Find the reagent, given the starting material and product. And find the product, given the starting material and the reagent. But those will be multiple choice test questions. So you'll have the answer in front of you, you just need to be able to find it. Okay?
Not on the final though, right? Or the big test?
The midterm?
Yeah, midterm and final.
Midterm has multiple choice questions. All right, some mechanisms. I'm not going to have you guys learn that many, or I'm not going to test you on that many. You'll be tested on potentially 4 addition reactions, SN1, SN2, E1, and E2. Let's go through the simplest first. Let's look at the SN2 reaction of hydroxide with 1 bromoethane, or just bromoethane. SN2 means second order. Both things are needed in the same step. Hydroxide attacks the carbon. Bromine takes the bond. Do you remember the rule I gave earlier? When bonds break, they break toward the more electronegative atom. Notice the bond breaking, it breaks towards the bromine. When bonds form, they form from the electronegative atom. Oxygen shares its electrons. That's it. That's the SN2. SN2 is a one-step mechanism. Let's look at E2 in the exact same compound where hydroxide does elimination with bromoethane. In E2, hydroxide doesn't act as a nucleophile so much as a base. It takes a hydrogen. Who owns the electrons between C and H? C. So when this bond breaks, it breaks towards the carbon, who shares them with its adjacent carbon, which allows the CBr bond to break. 3 arrows, 1 step. E2, a one-step mechanism. I'm trying to leave your other page for you. Easy enough? When we look at SN1 mechanisms, the only major difference is the number of steps involved and often the substitution of the carbon. So here we have a more substituted carbon and we have a weaker nucleophile. In step 1, the leaving group leaves. That's it. Now there are 2 ways that you can do mechanisms. One of them is fully sequential. The other is step by step. I am encouraging you to do whichever one you want. Fully sequential gets a little bit more complicated, a little more cluttered. Fully sequential just gets longer. But if you wanted to, you could say this is step 1. Step 2, and you can add these arrows here if you'd like to. Step 2 is the nucleophile attacking. Now, if I were drawing all of this out, at this step, I would explicitly show one of the OH bonds. The third and final step of SN1 in a reaction like this is the deprotonation of my alcohol and the formation of a conjugate acid. And there's something that I like to point out when I teach this in OChem 1, is that reaction 1A, or step 1A, would be carbocation rearrangements. This one didn't have a 1A. That carbocation never rearranged. In E1 reactions, step 1 is exactly the same. A leaving group leaves and a carbocation is made. Step 1A is the same. Carbocation rearrangements. None to be shown here. Now Now step 2 is a bit different because I have two bases, Cl- and H2O. Technically, H2O is a better base than Cl-. I don't care which one you show, as long as it's feasible. A base takes the hydrogen, the CH bond breaks to form a carbon-carbon double bond. Ooh, I put P on. Oops. Sounds familiar? Looks good? All right. You guys are good with the second order reactions? For the alkene addition reactions, the HX and H3O plus mechanisms are nearly identical. So I have you know these two mechanisms. I'm going to show you the HX, and I'm going to explain how the H3O plus is different. Step 1 is actually just acid-base chemistry. Oops. I'm sorry. We get this simple intermediate. The alkene takes on a hydrogen and a positive charge. A halide is formed. Step 1A, carbocation rearrangements, none to be shown here. Step 2, nucleophilic addition. The nucleophile bonds with the carbocation. Now, if X was water, there's a step 3 to deprotonate. Just like this. This step 3 was deprotonation of the water nucleophile. If you're doing acid catalyzed addition instead of HX addition, you just need a third step to deprotonate. That's it. Same mechanism, just one small difference. Then, if you have X2 or X2 in H2O or ROH, these mechanisms are nearly identical. With the exact same exception, X2 is 2 steps. X2 in a polar protic solvent requires a third deprotonation step. So I'm going to save us some time, and I'm just going to show us X2 addition. I actually gave you guys a bit of this on one of our first days when we talked about MO theory. One of the halogens gets attacked by the alkene, and that same halogen attacks the alkene back, breaking off a halide ion and forming a halonium ion, one of my favorite words to say. There is no possibility of a carbocation intermediate here. In step 2, the halide or the solvent, water or alcohol, acts as a nucleophile and breaks open the halonium ring. Notice the carbon that halide attacks is the carbon that breaks its bond. A bond forms from halide and a bond breaks to the halogen. If in H2O or alcohol, you need step 3, deprotonation.
Jacob, in step 2, will the halogen always attack the carbon with partially positive characters?
Which means the most substituted carbon.
Okay.
Although if you don't show it attacking the most substituted carbon, I wouldn't necessarily give you points wrong because you still get the same product. But if you don't, if you use one of these solvents, then it's not the halide that attacks. Because remember, for every halide ion, there are probably 1,000 molecules of your solvent. So your solvent overwhelms the ability of your halide to act as a nucleophile, and your solvent does. And your solvent, we said earlier, this was regio-specific. Your solvent must attack at the most substituted carbon. For the same reason, the halide also attacks at the most substituted carbon. But then you'd need to deprotonate your solvent. Just like this. I feel like if you can master these compounds, you can master any mechanism. I'm sorry, if you can master these mechanisms, you can master any mechanisms. I just don't think that most of the other mechanisms are worth our time. That's why I chose these. So if you're interested in mechanisms, go look at them. Google is just a few clicks away. Okay, you guys know about my YouTube playlist that I have my summer OChem 2 class recordings on. I also have my OChem summer recordings where I dive into spectroscopy over several days. I have 9 minutes to try and cover it here. So we're going to do the Cliff Notes version, enough that I think you guys will do well on the unit test questions. And like I said, I'm actually kind of reorganizing those unit test questions so I can make sure that what we cover tonight makes sense on there. So there's 3 types of spectroscopy that we're going to consider. And to be fair, we're not going to consider spectroscopy a ton throughout this semester, which is why I think it's okay to go a little bit easier on the unit test. But I do still want you guys to have an idea of what we're looking at. First of all, mass spec, IR, NMR. If you're not familiar with these already, you can actually find them on a website that's linked on our homepage called SDBS. It brings you to this, the Japanese Spectral Database, and you can put in just about any compound you can think of, except not any compound I can think of, because a lot of the ones that I want to use, they don't come up with. And then they sometimes have more than one spectrum for the same instrument, so you can play around with what different things will give you. I love talking about mass spec because we get to talk about magnets. But here's the general idea. Mass spec will shoot electrons at your compound and rip away one electron from your compound. If one electron is lost and the compound stays intact, then you create a molecular ion. These are most often formed when an electron is lost from a pi bond, lone pair, or sigma bond. Often in that order. So you guys had this question on active, and I'll just go through it. And it was saying, what happens when one electron is lost from this? Well, to be fair, I could take any bonding electron and I could remove it, and that would be a molecular ion. Notice that there's just a radical holding them together now. But it's much more likely that I lose an electron from that pi bond. 2 pi electrons, one gets removed, that leaves a hole, a positive charge, and a radical on separate carbons. No matter what your pi bond is, one carbon keeps the radical, one carbon keeps the positive charge. If you lose it from a lone pair, that atom keeps a radical and a positive charge. A daughter ion forms when an electron is lost from a sigma bond, and then one fragment keeps the radical, one fragment keeps the cation. So this is typically the mass of the molecule, m, minus some weight. The weight of the radical portion. Because the radical portion will not hit the detector, only the cation will. And that's your 1 minute review of mass spectrometry.
So it's only on the lone pair that you get the charge and the radical in one spot.
Correct. If you're looking at IR, I want you to be able to correlate absorption size, frequency, and shape with bond type. And I don't expect you to do this alone. On the home page of our course, we've got this correlation table that I made. It is a good approximation. On the left is the bond type. Then it describes the bond type. Notice that CH is not a bond type listed. sp2CH is listed. sp3CH is listed. And CH aldehyde is distinguished from other sp2CHs. That's because the orbitals that overlap to make your bonds change the nature of the bond, change how it interacts with IR light. Then in the second to the right column, you've got your frequency. When you look at a correlation, when you look at an IR spectrum, your frequency is listed down here from high on the left to low on the right, and your correlation table is organized from high frequency on top to low frequency on bottom. So if you wanted, you could print this out and turn it sideways, and it does a fairly good job overlapping. Then there's shape and intensity. You'll notice all of these are relatively sharp, but some are more intense than others. The peak on the left, fairly short. The peaks on the right, fairly sharp. Those are generally estimated in here. But IR is hand wavy. It really does depend on the compound and the instrument used to collect it. But here's the most important thing. 4,000 to 1,500 wave numbers is the most important range. This is the functional group range. This is the fingerprint range. That's a fingerprint. This is unique to a compound, but it's challenging to get specific information out of it. This is what most of your correlation table looks at. Now, the one that I always end up having the least amount of time to talk about, NMR. And remember, there's that playlist where you can talk more about it, or you can learn more about it. NMR, nuclear magnetic resonance, actually provides the most information about a compound. And its spectrum ranges from 0 to 12. On that correlation sheet on your homepage, I have this abbreviated correlation table. There are others that are the opposite. They are in depth. They are several pages long. They tell you the exact bonding environment of a hydrogen, where its signal will show up. This is hand wavy, but it is really good for approximations. You'll notice that carboxylic acids and aldehydes, aromatic rings, and alkenes are in very specific spots on the correlation table. So when you look at an NMR spectrum, you can say between 7 and 8, that is an aromatic ring. So chemical shift, delta, tells you your functional group. And then you have integration. These will be given to you. You'll notice they're not on here. That's things like 1H, 2H, 3H, which tells you how many hydrogens are making that signal. So it tells you how many hydrogens are in the compound. And then you have the splitting pattern, which is by far the most powerful piece of information and the least useful for most of our questions in this class. Super powerful, but you're going to get a lot more information from integration and chemical shift to be able to pick from a multiple choice what compound you're looking at.
So we will not have to draw it again on the test. It'll be a multiple choice option.
Yeah, there'll always be multiple choice.
Okay, fine, Jamie.
Yeah. Man, I'm so sorry. I want to talk more about it, and I kept you a minute over. Remember, if you're feeling stumped, especially when you find a question on active or on the unit test, where should you go? Back to the YouTube playlist. Look at somewhere where I spent more time on it. I think 1 class period instead of 9 minutes. So an hour and a half. Or look at my OChem 1 where I spend 4 class periods talking about it. If you feel like you're not getting enough information to answer the multiple choice questions, I've got really good resources for you on there. Or just email me and say, like, that's not a fair question because even your old videos didn't do a good job. Okay? I'm going to post an email tomorrow, or an announcement tomorrow morning about where we're at and what to be looking for in your unit test, and where to come, what we're going to be looking at when we come in next week. All right? Thank you for your time, guys. Have a good